And we started talking about this in the context of what makes an RF or ultra-high frequency circuit board different from a standard circuit board. We were talking about how the materials change. The loss tangent of the material, it's otherwise known as its dissipation factor, becomes ultra-critical. We've built circuit boards operating as high as 110 gigahertz. Typically, when we start getting into those requirements, we start talking about requiring the ultimate in low loss. In that case, it was extremely low dielectric constant material, utilizing a very high conductivity rolled copper foil. You see at those frequencies, even the structure of the copper itself starts to play a big part in how the circuitry ultimately functions.
Yeah, because basically the copper acts as a typical line transmission, so all the formulas and technology we know about line transmission also applies for the coppering and the copper on the PCB, the printed circuit board.
Exactly, and we also got on the subject of line definition. When we start talking frequencies outside of the digital realm, we start getting concerned with the shape of the traces as well. We were talking about different etching methods, ammoniacal etching versus an acid cupric chloride etchant, and how it alters the actual shape of the edges of the circuitry. When we start talking about other various structures, we start talking about some of these filter structures, and you notice there's actually varying width gaps in these filter areas designed to pass a certain frequency or to exclude a certain frequency. The actual shape and the height as well are key factors in that. What the most key parameter that I see RF engineers being aware of nowadays is the specific circuitry height. How tall is my copper? In the old days, everybody was just concerned with how much copper you had in the holes of those types of PCBs. Now they want to control the overall plated thickness or the resultant height of all the circuitry to a very fine degree. This starts getting into plating distribution across the panel, and when we start running some of these projects in volume, we start talking about larger panel sizes, 18 by 24, as large as 21 by 24 inches. And if you understand electroplating, to some degree, you'll understand that the current density is never the same across the entire panel, and so you end up with varying circuitry height from edge to center to edge, and it can even differ from top edge to bottom edge of the panel orientation within the plating cell itself. So it is working on minimizing the variation across all those plating cycles. With sequential laminations and sequential plating cycles, we're in essence taking some of these substructures of a circuit board. Let's say, for instance, an 8-layer circuit board. It could be constructed as a layer 1 to 2, 1 to 4, 1 to 6, 1 to 8. That's an extreme example, but in that particular instance, we're actually plating layer 1, which could have our critical RF circuitry, or conversely, it could have very high density digital circuitry on it. We may end up plating it 3 times. And so we end up with this great increase of the copper thickness, and the resultant variation is exacerbated just by that. So controlling those factors and reducing overall copper buildup on today's circuitry is becoming increasingly important.
What I find fascinating to hear is that basically we see a PCB as a sort of a carrier for components. With RF technologies, basically the PCB becomes also a component itself.
Absolutely.
And that is very interesting to hear and to see how that moves forward.
And you see a higher integration of that in some of these other products. These are actually components that get placed on a circuit board, but they are circuit boards themselves. Some of these are filters, some of these are couplers, and basically I don't have a particular example with me, but oftentimes you'll see these get mounted onto a circuit board as a component. So it'll be a circuit board with multiple circuit boards on it, because these are very tightly controlled, very tight specification control to yield precise filtering or coupling, for frequency control, or for amplifier or some other functional control of an RF system.